So welcome everyone to the Wednesday Applied Algebraic Topology Research Network seminar. The speaker today is Andrew M. Thomas, and the title of his talk is Functional Limit Theorems for Euler Characteristic Processes.
I guess I'll take it from here, right?
Yes.
Okay, perfect. Yes, so I'm Andrew Thomas. So I add the M in there because it's not a terribly distinctive name that I have. So just want to distinguish myself a little bit more. But anyways, so today I am going to be talking about some of the work that I've done with my advisor, Dr. Takashi Iwata, on some functional limit theorems for Euler characteristic processes. So as tantalizing as that title is, I'll get into that as we go along in the talk. Before that, though, I just want to discuss a little bit of what the setup is, generally, what sort of stochastic elements there are in our work and my work and what's going on. So let's just get started with some of the motivation. So we take a finite point cloud. So this is a setup that probably everyone's familiar with. And, these are the topology of these points, or the homology, or whatever you want to look at, is not terribly interesting. In the typical setup, each of these points in this point cloud are independent and identically distributed with, say, a probability density F. At least in our setup and in a lot of other setups, this F is taken to be bounded. There are other further restrictions that you can put on it. So one way to get some, measure of the shape of these points is to look at the Euler characteristic of this point cloud. Well, if you look at the Euler characteristic of this, finite discrete set, that's just going to be n if your cardinality of your set is n here. So that's pretty boring, and that doesn't give us a lot of insight into the shape of the support of the density or anything else. And typically, at least in our setup currently, we want to look at the support of the density. So the support is where this probability density is greater than 0. So if we continue on, one way to fill things out in this point cloud is to add some sort of shape to it. We need to fill it out to get something non-trivial. So what we have chosen for this project is the Vietoris-Rips complex. So the definition of that is, again, probably familiar to most folks. But if you have a finite set, the Vietoris-Rips complex is just the combinatorial abstract simplicial complex of subsets where a simplex is in that set if and only if the pairwise distances between the points are less than some threshold. In this case, 2t. So if the balls of radius t around each point intersect in a pairwise manner, and you can see here the evolution of how that behaves as you increase this radius around these points. So you can see in this instance, when t is equal to r, you just have a few edges and a lot of other points. When t is equal to 1.5 r, whatever r might be, you can get a 2 simplex in there, so you can get this triangle filled in. And then when you get to 2r, you get some tetrahedra in there, which makes things really difficult to embed into R2. Okay, so now that we're thinking about summarizing shapes and we've decided on the Euler characteristic, what can we do from here? So there are two separate definitions. Now, the Euler characteristic is infinitely definable. There's many different ways. There's the Euler polyhedra formula. There's ways that you can define this in terms of critical points of Morse functions from a manifold. But we only choose 2 here, a very foundational result. So I don't want to, speak like this is a trivial result, but we use this to great advantage to get an insight into the shape of these points, right? or the Vietoris-Rips complex around our point cloud. So one way we can define this Euler characteristic is in terms of the k-simplex counts. So as you can see here, the Euler characteristic of this simplicial complex is just the alternating sum of the k faces within this simplicial complex. So k face is a k-simplex, k plus 1 points that satisfy the diameter condition that I had mentioned earlier. Another way to do this is in terms of the alternating sum of the Betti numbers. Again, I mean, this is a beautiful result. And you can look at the Betti numbers of these, this simplicial complex. So you can see basically from this combinatorial structure, you get this shape structure, and it's very nice. And the Euler characteristic turns out to be a homeomorphism invariant. So if you have some topological space Y, and you have a homeomorphism between that and the geometric realization of, let's say, some abstract simplicial complex, or if you have, some geometrically realized simplicial complex, then, the triangulation is just a homeomorphism, and it's independent. The Euler characteristic of that space is independent of the homeomorphism. Okay, so you can see here in this image, the homeomorphism between this triangulation of the two sphere. So in this instance, the icosahedron, which is an illustration in itself of Euler's polyhedron formula, and the Euler characteristic of the sphere. So essentially, this is just a visualization of these two formulas right here. Okay. So again, just to let you know what the Euler characteristic is here. You can see some of this, but I won't spend a lot of time on that. So just take a snapshot with your eyes, and then let's head on. Okay. Now we're getting to the point where I feel a little bit more comfortable. The water's a little nicer here, at least from my perspective. So basically, as I had mentioned, maybe I didn't mention it. I'm not sure. It's immaterial. What we do instead of just dropping points down, let's say n points randomly, is we, at least in the random geometric complex literature, drop points down according to a Poisson process, which allows you to get this really nice spatial independence property that's down here. So what that means is if you have a Poisson point process, it's a random subset of RD. You can also identify this with some random point measure or counting measure. And the number of points within any set, Borel set in this Euclidean space, is Poisson with parameter lambda A. And lambda A is some intensity measure on that space. It could be some constant times Lebesgue measure. It could be something like some constant times a probability measure, which is what we use in this case. But it can be very versatile. And I should say that you can define a Poisson process on a lot of different spaces. It doesn't have to be Euclidean space, but we just focus on Euclidean space here. And then, of course, you get the spatial independence property. So you get independent random variables for independent sets. So, if you look at the, upper orthant or whatever, and then some other disjoint set, the number of points in those two disjoint sets are independent.
And so, Andrew, I guess this is different from choosing exactly n points, because if you chose exactly n points and you had a lot in the top left, then you'd have on average fewer in the other chord. I see.
That's exactly right, and that presents some issues when you get to proving things like functional central limit theorems or central limit theorems in general, because at least in the method that we've used, it's harder to get some independence in, like, whatever method you're using. Typically Stein's method, or you could use some Malevin calculus stuff. Regardless, that's not that important, but it makes it more difficult. You can de-Poissonize, which is used to great effect in the literature, to take a result, a central limit theorem, for some geometric functional of a Poisson process and turn it into one for, those n independent points. But we don't worry about that here because it's highly technical and doesn't really, the results don't differ besides maybe a little bit of a change in the covariance structure of your limit. So it's not terribly important in terms of the gist of the result. Okay, so that's the Poisson process there. So I'm going to discuss a little bit of the literature to say, okay, why would you want to look at the Euler characteristic of a Rips complex, based on some time parameter? What would get in your head to make you want to do that? As Henry had mentioned, a common setup is where you have NIID points with probability density F. Another common setup, and one that we use, is where you have a non-homogeneous Poisson process, so non-stationary. So what that means is that your intensity measure is not some multiple of Lebesgue measure, right? So in this case, it's n times probability of whatever is in that space. So over all of RD, then you'd get n points on average. That's the expected number of points you would see. And we just want to briefly mention the check complex, so we don't deal with it here because the check complex does, and I'll mention this later when we talk about the functional central limit theorem, but it does present problems in terms of proving what's called tightness for the measures associated, for the probability measures associated with the Euler characteristic processes. Okay, and then finally we need to define a sequence of radii for these complexes, which we just generically take to go to 0 as n goes to infinity. Okay, so the first result, and I'll say maybe, one of the earliest ones, at least to my knowledge, in the random geometric complex literature. Obviously, the Euler characteristic has an illustrious history in other domains, but in the random geometric complex literature, the Euler characteristic over the check or Rips complex, I think this is one of the first results. So what this says is that when you have the radii going to 0 fairly quick, so you can sort of think of these NR and D as the expected number of points within any ball of radius Rn. So the expected degree goes to 0 here. So essentially what you're going to get is just isolated points. This is actually not correct. There should be an n to the -1 here outside. I just realized that. But it scales with n. So essentially when you have n to the -1 times this expectation, all you're going to get when the radii are really small are just these isolated points. When the expected degree is going to some constant, then you get you get a complex structure here. So you get, obviously just your isolated points here are your 0 simplices, but you get something else for the other, the critical points, as it turns out. They use a critical point approach here. So, what's called Morse theory for min-type functions. And then in the supercritical regime, the expected value of this Euler characteristic on the check complex goes to 0, so it's sub n. So basically, you get a lot of, contractible bits within this check complex, and the homology sort of vanishes. If you take the radius even larger than this, so if the radius is greater than some constant times log n, this expectation actually goes to 0 itself. Or no, the expectation actually goes to 1. Because in that case, your check complex is going to be contractible itself. But in this case, at least in the supercritical or dense regime, they assumed that F has a compact convex support, which is, I think, pretty important for proving that that space is covered. Okay, so that's I would say pretty important to what we're trying to prove, but yeah. Okay, so anyways, there's a lot more literature, but I'm going to talk about other cases where you have maybe a different point process. In Yogeshwaran and Adler 2015, you see that this n to the -1 times the Euler characteristic of the Czech complex on some well-behaved stationary point process with intensity measure n times the uniform measure on the unit cube has similar behavior roughly to what we saw here. So in the sparse and critical regimes for which it's proved, you get essentially an analogous or the same, except with differing sort of constants or integrals right here for the gamma k for this Euler characteristic based off the Czech complex of the stationary process. Another case is the de Croisefond et al., which instead of using a critical point approach, like the Yogeshwaran Adler paper used and the Bobrowski and Adler paper used a simplex count approach, which is the approach that we take here. And so they do a similar thing, but they just show using the L infinity distance, and they use some techniques from Poisson processes and Malevin calculus to derive some exact results, which are really nice. So actually for one of their results, they can get an exact formula for the Euler characteristic. Just because of the structure of the L infinity distance, it makes it relatively easy to get an insight into some of these integrals that pop up in the limit when you're looking at, the expected probability of a simplex forming or something, for example. So you can get this, and then actually right down here, if you look at the infinite sum, this is actually some quantity times a Touchard or a Bell's polynomial, which is related to moments of the Poisson distribution. So that's kind of interesting. But what they also showed was they gave exact formulas for the variance for all d, the variance of this Euler characteristic based on the simplex count, and a concentration inequality as well. So meaning how much does the Euler characteristic deviate from its expectation. So actually what we do later for the functional central limit theorem is give a central limit theorem for this deviation from the Euler characteristic to its expectation. Now, I'd be remiss if I didn't talk a little bit more about some other interesting things that happen with the Euler characteristic. I know that Keith Worsley did a lot of sort of applied work with the Euler characteristic in the 90s and up until the early 2000s. And there's a lot of other work in random fields, essentially. Not essentially, but it's just there. And there's a lot of beautiful formulas looking at the Euler characteristic of super level or incursion sets of Gaussian random fields. And a lot of this is due to results in stochastic geometry or using the Euler characteristic as a intrinsic volume. So that's how it's considered in this instance. Again, speaking to the manifold definitions of the Euler characteristic, pun intended. And theorem 2.1 in Hug-Last and Schulte gives a central limit theorem for all these intrinsic volumes. So, you can easily project down to the Euler characteristic and get a result there too. So as I had alluded to, a lot of the results use Morse theory and modified, especially in the Bobrowski Adler and the Yogeshwaran Adler papers that I had discussed, use a sort of modified version of this Morse theory to account for the fact that the distance function is not always continuous. Okay, so now let's get to some more of the ingredients now that we've perhaps whetted your appetite for some of the previous results that are out there, and why you would study what the limit of the Euler characteristic of some simplicial complex is. So we want to start out right now with discussing a little bit about weak convergence. So in general, for some metric measurable space, weak convergence is most, I guess, versatilely defined in terms of functions, but you can also consider it in its maybe most intuitive sense as the convergence of the distributions, right? So you have your probability xn is in some Borel set A going to the probability that x is in A, and then you say that xn is, you know, converging weakly to x. Now, there's some conditions on the measure probability x and A that you have to have, namely that the boundary of that set with respect to the probability measure has to be 0. But that's, you know, that sort of obfuscates the intuitive nature of what's really happening here when you have probability of xn in A going to the probability of x in A. X converges weakly to x if, you know, the expectation of fxn goes to expectation of fx for every bounded continuous function there. Okay, great. So now we get into the weeds a little bit more with some more analysis, which I'm sure all you. So D0 infinity is what's called a Skorohod space. So if you were to think about the Euler characteristic, well, if you looked at the if you took a Rips filtration or a check filtration, choose a filtration, and you apply that Euler characteristic to it, then you're going to have a bunch of jumps, right? Because the Euler characteristic is manifestly not continuous, right? I mean, you're going to have jumps in terms of how many cycles are present, how many simplices are present. I mean, you know, you're just going to hop up and down all the time. However, this process is right continuous. So if you had, you know, a set of points with diameter t, then, you know, the indicator that represents whether, you know, that set has diameter less than t is going to be satisfied until you get right below t. So it's going to be, you know, your typical right continuous left limit type thing here. So as you see on the left in this image. Now to prove weak convergence in this Skorohod space, you kind of have to do some difficult things. You can't just use functions from this, you know, function space of CAD-lag, right continuous left limit functions. You have to do something typically different because it's just harder. I mean, those functions are not very intuitively defined. So what you typically do is you prove finite dimensional convergence, and then you show that that sequence is tight. So I had mentioned earlier that one of the reasons why we use Rips complex in proving the functional central limit theorem is because the Rips complex has a nice structure that allows you to prove tightness, which essentially means that you know, for any epsilon, you can find some compact set in this Skorohod space such that the probability of, you know, every element of the sequence, you know, has high probability on this compact set. So you have to prove finite dimensional convergence and then tightness to prove this functional central limit theorem or functional weak convergence in general. Again, it's unnecessary, but it's just typically, practically what always is going to happen. And you'll prove that for each of these time points, at least in the finite dimensional sense. Okay, so what is a Skorohod space? Well, you have, you know, if you have Fn, this is funky, but if you have a sequence of functions and some other distinguished element of the Skorohod space, then this function Fn converges to F in the Skorohod metric if you can basically wiggle time a little bit so that the functions are converging uniformly. So if you have uniform convergence, then you have convergence in this Skorohod metric, which is important for what we talk about with the functional strong law of large numbers that we prove. But you basically have these surjective, so the bijections between, this compact interval 0 to t, and then, they have to be strictly increasing. Well, that implies bijective anyways, but yeah, and then the lambda n functions have to converge uniformly to 0. And so if you can find that, then you have convergence in the Skorohod space. Now, when you're looking at convergence weakly, so the weak convergence or convergence in distribution that we were talking about, a similar thing happens. So if you can show that restricted to the time interval 0 to capital T, if that converges weakly for all those intervals, then you've shown weak convergence over D0 infinity. And this is easy to prove. You just show that for every T when your limiting process is continuous. So if you want a reference for that, you can look at Patrick Billingsley's famous Convergence and Probability Measures book. It's nice beach read.
Andrew, a question. So
Sure.
These are functions defined from 0 to infinity. Those are the inputs.
Yeah, so they're real valued.
In your case, are these functions going to be the Euler characteristic and the input's going to be the scale in the Rips complex?
Yeah, so I think like maybe the next slide, I'm going to discuss the Euler discuss where the time parameter comes in. Yeah, I'll tie it all up. Don't hesitate
I trust you.
to yell at me if I don't get that worked out. Yeah, right here. All right. So in our work, we've assumed that X is this point cloud that we have is generated by a Poisson process. So it's, instead of n points, it's a Poisson n number of points. So on average, there are going to be n points put out there, but theoretically there could be any natural number of points, right? So the Poisson variance isn't very large, so practically it's going to be kind of concentrated around n. The intensity measure, so the expected number of points within any Borel set, is just n times the probability of the random variable being in that set. And the one condition that we've allowed on our F is that it's almost everywhere bounded. So to tie this all in with the Skorohod space, we parameterize Rn. So you remember in the previous cases, what's been proved in the literature so far is you just have some Rn, some sequence. Well, now what you can do is you can say, let's fix an n. So we have a large sample, right? And a small radius there, some arbitrary small radius. Well, now what we can do is we can look at the behavior of this Euler characteristic across a range of t. So we can get more information, essentially. That's what we're trying to do here. So when we're looking at the limiting behavior of x and t, t is the parameter of this random function. So chi n, not xn, is a random element of this Skorohod space. So it's a random function from 0 infinity to r, right? So that's where the parameter comes in. So this RNT might look a little artificial, but it's actually, this sort of same parameterization has been used in proving functional limit theorems for instance, k-nearest neighbors distances. So typical vertex degrees in like the random geometric graph context. So actually, I mean, a lot of the limit theorems in the literature in random geometric complexes come from sort of the graph theoretic limits from, Penrose's monograph, Random Geometric Graphs, and all of the surrounding literature around that. Okay, so we have our chi chi nt here, and then we have our RNT, this parameterized radius. So what happens? I sort of alluded to the fact that this depends on the this Sn, and the Rn is a measure of the expected degree of the graph. I'll elaborate on that a little bit. So they're called regimes. No political power, thankfully. But when you have this row n equal to 1, then you get simplices of dimension greater than k disappearing in probability. And you get a Poisson limit for, let's say, the simplex counts. In the second case, which is often called the central limit theorem regime, you get the radius, the expected degree going to 0, but this n to the k plus 1 Sn dk going to infinity. So there's enough to sort of support a non-totally sparse structure there, so that you can get a central limit theorem. The simplices greater than k don't necessarily disappear in probability, but I think, no, this should be less than or equal to k right here. They don't necessarily disappear in probability, but the simplices less than or equal to k dominate the contribution to the Euler characteristic.
Andrew,
yeah.
Sorry for the interruption. What is Sn?
So Sn is so the radius of our Vietoris-Rips complex. So the diameter condition, or the pairwise distance condition that needs to be satisfied for simplex to be included in our Rips complex, is that the pairwise distances are less than 2 RNT, and RNT is equal to SNT. So Sn is just sort of the behavior of the radius.
Okay. So okay.
It governs the limiting behavior of the radius. Does that?
And then Sn goes to 0 as n goes
Correct.
to infinity, according to those regimes on your next slide. Is that right?
Yeah. Sn goes to 0, and then the expected degree goes to other things. Essentially, you're doing a calibration, right? You're putting a lot of points down, and then you're sort of making the ball smaller. So you're more or less calibrating the space. You can get a better resolution for what the shape of your support is, right? But the behavior of like what that eventual calibration is going to be depends on these NSND quantities here. And then what we focus on is the thermodynamic regime. So when you have a simplex count, this is really important because otherwise it's a little bit difficult to deal with. But if this NSND is equal to 1 or converges to 1 at least, then you can just scale by n, because this nk plus 1 SNDK divided by this what is it? This quantity, no, just divided by n is going to get some constant, right? And anyways, in the dense regime, you just get a highly connected graph, and the expected degrees go to infinity. So the intuition behind this, let's see. The intuition behind this SND, which I've talked about a lot, can actually be derived fairly easily using just a simple change of variable here. And you can see that this NSND sort of pulls out. So if x is in the support here, then this quantity will go to some constant, you'll get some constant here if you're like in our regime, the NSND goes to 1, or this this ball size, whatever you want to call it. NSND isn't very pithy, I guess, but yeah, so you're going to get the expected degree on the order of NSND in the Rips and the Czech complex, because of course the Rips and the Czech complex have the same one skeleton. Okay, that's good. So finally, I can present some of our results here. about the Euler characteristic process. So, like I said, we only considered the thermodynamic regime based on sort of the scaling limits in this case. Now, like I had mentioned with some of the previous literature, if you look at, let's say, critical points, you're only going to get up to index D critical points because that's the nature of them. You know, in terms of Morse theory. But in this case, when you represent the Euler characteristic as a sum of the alternating sum of simplices, you can have any large number of, you know, simplices. I mean, you can have any arbitrary dimension, arbitrarily large, which makes things difficult in terms of scaling the limit. So what you want to do in this case is, I guess, look at the thermodynamic regime. But the thermodynamic regime is also considered, I think, fairly applicable or fairly practical, fairly useful, because, you know, most of the time you're not going to have super connectivity or anything like that. You'll have a graph that's relatively well connected, but not too highly connected, which is what you'll see in this case. And then, as I had mentioned, we have the Euler characteristic of the Poisson process. I'll promise to stop mentioning that I've mentioned things. Anyways, so the two things that we do is we prove a functional strong law of large numbers, which I'll get into, I think, on the next slide. And yeah, of this n to the -1 chi n t, and then the central limit theorem for the centered and appropriately scaled chi bar to the t. And then we want to define this ht of k+1 points to be the indicator that these points form a simplex in the Rips complex. Okay, so our first result that we were able to prove was that when you equip D with the uniform topology, which, as I'd mentioned, implies convergence in the Skorohod topology, because, I mean, for that function that wiggles time, you can just choose the identity. Then you're done. But you get uniform convergence to this very, very nice analytic function. So if you can get some idea of what your density is, so let's say you have a uniform density on some bounded set, or any set really with finite measure and non-zero measure, and you can, you know, figure out what this ht is, and you can get an explicit representation for the behavior of the Euler characteristic, you know, of these random points as n goes to infinity, which is kind of nice, actually. So to elaborate a little bit about what this functional convergence means is that, so if you pick a sample point, so, you know, any sort of sample that you choose from this Poisson process, then you're going to exhibit this uniform convergence to this, you know, lovely squiggly line that represents the analytic function that this chi n t over n converges to. So on any interval 0 to t, on any compact interval, I believe it still holds. And actually, when you as I alluded to with the de Croisefond article, if you use the L infinity distance, so our results hold with any norm. When you're uniform on a set A with Lebesgue measure less than infinity, you can derive this nice little formula here in terms of the Touchard polynomials. And yeah, I think this might, yeah, I don't know. I might be missing a D here. Not entirely sure, but you can get a nice representation for it, because you can take this integral right here of the hkt, and you can tensorize this L infinity distance. So you just, you know, take all of these y's to lie in R1 instead of RD, which is a nice result. So you can get this nice distance, and you can see for these curves, let's say you had an Euler characteristic process here, and you scale by n, then the Euler characteristic process would converge uniformly to these curves. So if you, for example, if you had f uniform on the unit cube, and you were forming this Rips complex based off of the Manhattan or L infinity distance, then you would get sort of uniform convergence to these curves here. Now, actually, Omer Bobrowski gave a talk in December about homological percolation in the Euler characteristic, and in that talk he mentioned that these there's strong evidence and recent evidence shows that these correspond to changes in homology, where a certain homology group becomes dominant, and you can certainly see that, you know, when you're in 2 dimensions or 3 dimensions, the number of zeros correspond to the number of dimensions as you might expect, based on when you know, a certain Betti number takes over. So you see these cool little heartbeat curves, and there's a lot of classes of densities that you can find this for, you know, as long as you can evaluate the k+1th power of the density. I mean, as if that's a tractable thing. And in the Gaussian case, you can do that too. But this is just when they're uniform. So you can get these nice little curves here. Okay, so now our last result is the functional central limit theorem. And if you remember what this chi bar n is, it's this centered and scaled Euler characteristic process. So what we have is that this chi n converges to a zero mean Gaussian process in Skorohod space. So what that means is that each finite dimensional distribution of chi bar n converges, and this sequence is tight. So what I communicated was that the Rips complex is sort of essential, or at least was essential in our proof to proving that this chi bar n is tight. And then this Gaussian process exhibits a similar structure to the Euler characteristic. So these script HKs are also zero mean Gaussian processes, and they sort of correspond to the spatial distribution of the simplexes. So the deviation, the individual scaled deviations from, you know, the k simplex count from its expectation. So you see a mirrored structure in this limiting Gaussian process to the structure of the simplex, or the Euler characteristic itself. Okay, so that's sort of interesting. Now, to maybe elucidate a little bit what this means, script t, or script h of t, is normally distributed with this variance that's a double sum of these alternating integrals of the essentially what is some expectation of the behavior of mutual simplex formation. So when there's, you know, one complex and you know, with radius t, and you want to look whether that forms a simplex, but simultaneously you want to look whether some other points are forming a simplex and they have points in common. This is a sum of those integrals, and this you know, uppercase psi k1 kt depends on the density f as well, but only through the integral of these powers of f. So these moments of f, if you'd like. So f k1 plus k2 plus, you know, 1 minus j, or 2 minus j. So you get this sort of interesting structure here, and what's sort of bizarre is that there's a negative sign in this variance, and the variance can't be less than 0. So that this has to be positive. Now, another thing that we proved in our article was that the limiting Gaussian process is continuous, and the sample paths are locally Holder continuous. So you know, there's a random variable such that you know, for every t minus s less than that random variable, you have Holder continuity. So x or script ht minus script hs is less than the distance between some constant times the distance between t minus s to the power y, or power gamma, and gamma is between, you know, 0 and 1/2 exclusive. So yeah, so that's sort of interesting. What we can say, or why we care about this convergence is actually sort of relevant to statistics, believe it or not. You know, data analysis in a topological sense, for example. So for any t, what we can do is we can, yeah, there's a mismatch here between the t's and 1s, but for any t, we can take this supremum map and look at the supremum of these differences. So you can look at the supremum of the Euler characteristic, and that converges because this map is continuous. You can also look at the supremum of the deviation from the expectation, and it converges to the supremum of this Gaussian process. So a well-known result in statistics and probability is the Kolmogorov-Smirnov test, where your empirical distribution, so the number of your random variables less than t, minus f of t, the supremum of that goes to a Brownian bridge, so some Brownian motion conditioned on, you know, I think W1 equaling 0. And from that, you can test distributional assumptions. So by proving these functional strong laws and functional central limit theorems, there's perhaps a hope that you can do some goodness of fit testing. So there's actually some other results about goodness of fit testing that I know of in an article recently published, I think in the Electronic Journal of Probability, by Bicio, Christophe Bicio, I think, et al., about using Betti numbers and proving functional limit theorems for persistent Betti numbers to you know, test the goodness of fit of a point process. So ideally, what you can do is, you know, if you have some density, you can see, well, you know, does it behave like a Gaussian process when you subtract off some expectation you might think it might have, and hopefully you can maybe do some statistical tests. Regardless, you know, you can't expect in mathematics that your results are always going to be practical. So at the very least, it's a nice and new result. So that's good news. So as a final addendum, I guess we're getting to the end here. Perfect timing. Future directions are looking at functional central limit theorems, or functional strong law of large numbers for the Euler characteristic in what's called the extreme value or crackle case. So there's been a lot of work done on this by Dr. Takashi Iwata and Robert Adler, among others, looking at the behavior of the topology of random points, or check complex or Rip complex of random points outside of a growing ball. So obviously you can't have a distribution with compact support in this case, otherwise there will be no points eventually. So practically what you look at is a heavy-tailed or light-tailed distribution where you are going to see extreme values with some relatively reasonable probability. So we've proved the functional strong law of large numbers for the heavy-tailed and light-tailed cases here. So that's definitely a future direction to go in with regard to the Euler characteristic process. You know, another obvious direction to take it would be to look at the Euler characteristic on Euler characteristic process supported on a manifold instead of just ambient Euclidean space. As I discussed earlier with this extreme value theory case, F is spherically symmetric, or at least assume so, but you don't necessarily need to have that. You can relax. It just makes the proofs a little bit easier. And then you have this sort of critical regime type thing too, except that instead of Rn d, the radius of this, you get the density, at this radius of the growing ball goes to some constant. So again, you see that the critical regime makes it easier, at least because in this case, we again choose to represent things in terms of simplex counts, and it's much easier to prove things in the thermodynamic regime when you have simplex counts. Based on that rho n, hopefully you remember that. Okay, and then the last question that I brought up was how might one apply this all to data and use some of these probabilistic results to help data analysis move along. I don't know. Don't spend a lot of my time thinking about that, but it's all very interesting to me. So yeah, these are just a few directions in which you can take the Euler characteristic process, but I think there's a lot of other different setups that you might be able to find that have relevance, especially with the tie-in with homological percolation, and when certain homology groups take precedence over the others. I think that's it's a very interesting connection. So being able to just sort of work in that space is I don't know, neat, right? So yeah, that's all I got.
Thank you. So before we get to questions, I would ask everyone to unmute themselves so that we can thank the speaker and clap.
Thank you.
So we actually had one question. So I'm just going to start because there was one question that came up just as you were, like before you were going to your conclusion slides, namely the Kolmogorov-Smirnov test. I decided not to interrupt you then because I figured you're going to be fast.
Sure.
So the question is there a way to use the result on the Kolmogorov-Smirnov test to get a Kolmogorov-Smirnov test on a manifold or multivariate Euclidean space?
Huh. Could you repeat that? I'm not really.
Is there a way to use the result on the Kolmogorov-Smirnov test to get a Kolmogorov-Smirnov test on a manifold or multivariate Euclidean space? Yeah,
I think that not that I'm aware of. I think that the Kolmogorov-Smirnov test at least is very sensitive to univariate distributions. So I don't think it generalizes very well to multivariate distributions. I could be wrong, but I think that yeah, the dimensionality of it is an issue, which is why people look at different things like nearest neighbor distances or k-nearest neighbor distances.
So Cheyenne asked the question, want to add anything to that?
Sorry,
Sure.
what's that?
I guess what I was wondering is, yeah, that's right. The Kolmogorov-Smirnov test, it's very hard to generalize it beyond one dimension. But I was wondering if you could think about this Euler characteristic perspective, if that would be more natural to generalize to higher dimensions.
Yeah, I would think so, though. One of the thorny aspects is that you see this density, the density F pop up in the limit. So it's not entirely clear how you would maybe be able to remove that. I mean, maybe taking the supremum like you do in the Kolmogorov-Smirnov setup and mapping that might be a similar way, but I don't know what the representation of the limiting Gaussian process would look like, or its distribution would look like if you took the supremum of it.
Okay, thank you.
Does that answer your question?
Yes, exactly. Thank you.
Okay, good.
Okay, more questions. So remember, you have to unmute yourselves to ask a question.
I have a question.
Sure.
So can you tell us about functional central limit theorem or functional law of large number for Betti numbers, not the characteristic function, but Betti numbers?
Yeah, right. So actually, in a previous paper, we had done some of that, and we cited your paper actually. Yeah, I mean, as you probably know, it's difficult to do that because at least in our case, we had to restrict the time. So the time parameter had to be restricted to get even a finite dimensional convergence, much less a functional convergence. So I'm not sure. I mean, maybe you might be able to do show some sort of functional central limit theorem for a Poisson or sparse regime, but I haven't looked into it too much.
Okay, thank you.
Yeah.
Okay, more questions for Andrew.
You mentioned how check complexes, it's harder to prove this tightness. Can you say a little bit, I don't know if there's anything to say about why check complexes are so much harder in this case than Rips complexes.
Well, so I guess I'm not sure why it's much harder, but I guess I should emphasize the fact that it's much easier in the Rips complex case. So what you can do is, in proving tightness, you have to look at integrals of these like complex formation, right? So you have some indicator times some other indicator, but the indicators like a K-simplex is formed at radius t, but not at radius s. So t is greater than s, and for points that are not necessarily disjoint or actually not disjoint, you have radius formation at s and not at r, or not radius formation, K-simplex formation at s and not at r. So you have to find out a way to integrate that. Well, in the Rips complex case, what you can do is you can just say, well, if this happens, then there has to be some pairwise distance that's between 2s and 2t, right? And it has to be less, there has to be another one that's, you can just ignore the s and r part too. So yeah, the fact that you have a Rips complex is nice because you can just sort of use the countable additivity of measures to say, well, there's got to be one pair that satisfies, this is in the K-simplex, but it's not, going to satisfy anything in the s, s radius K-simplex, I guess. So does that clarify things a little bit?
Yeah.
A little muddled.
So, more questions? I think we have time for one more if there is a question, but if not, then we can just finish now.
Oh, okay, so I just have a comment.
Sure.
So, so actually, there is an extension of your result to the case of check by Krebs. Maybe you know.
Yeah.
They show the tightness for the check case.
Oh, really?
Yeah.
Okay. That's
so just a comment.
Yeah, that's good information.
Okay, so thank you very much for joining, everyone. The next time we meet is on Monday at 11 a.m. Eastern time, 5 p.m. Central European time, or wherever you are in the world. And I wish you a nice week. And thank you again, Andrew.
Thank you, Henry and Sarah, for having me. Appreciate it.